In this video, we're going to be looking to solve a neat little problem that I found in an old maths challenge, and then I'm going to test you by posing a few more problems that will test how well you understand the general patterns here. Please leave your answers in the comments below. So before we tackle the problem, let's look at the facts that we're going to use, and I'll show them to you in a grid. So when we add two even numbers, the answer is also even. When we add two odd numbers, the result is also even, and an odd with an even is odd, and likewise for an even plus an odd. Now for multiplication, it's slightly different. In fact, the product of an even with any integer is even, so only when an odd is multiplied by an odd do we get an odd. Right, that's all we need. In the diagram on the right, how many squares of any size are there whose entries add up to an even total? So when they say a square of any size, you could have something like that as well. Now, the way to solve this is to rewrite the grid where you don't actually care about the exact values, you only care about whether they're even or odd. So I'm going to rewrite this grid just like this, as a whole grid of odd then even, then odd then even. Now we can go about systematically counting. So let's just start with the smallest squares, which are 1 by 1 squares, just to be a single entry. Well, it's easy to see here that half of them are even, but because we're dealing with the odd total is 25, only 12 of them are going to be even. So we've got 12 1 by 1s. Now let's look at 2 by 2, but we can be a little bit smarter here. Notice that every 2 by 2, no matter what I choose, will have two odds and two evens. And because we've got an even number of odds, because we've got two odds, we know they'll all be even. So we simply have to count the number of 2 by 2 squares. Now, this is a separate problem that often comes up, but I'm just going to skip this and give you the result. There is 16 2 by 2s. Now, let's have a look at a 3 by 3. We can still be a little bit smart here. Let's have a look at this 3 by 3. It has 5 odd numbers because there's one in the middle. There's this one in the middle. So because it's got an odd number of odds and thus an even number of evens, the total has to be odd. So we know that we just can't have a 3 by 3 that's got an odd in the middle. So that makes it very, very easy. There's this 3 by 3 that's got an even in the middle, this 3 by 3 that's got an even in the middle, this 3 by 3 that's got one, and just one more. And it makes a nice little pattern. So now we know we only have 4 3 by 3s. And then the last thing is a 4 by 4. Now a 4 by 4 is made out of 2 by 2s. So we know that the sum of a 4 by 4 just has to be even. So how many 4 by 4s do we have? 1, 2, 3, and 4. So we've got 4 4 by 4s. Let's add all of these up. 12, 16, 4, and 4. I believe the total is 36. So the answer is D. Let's have a look at the first extension question. The first extension question is simply, can you do the same problem, but for a 6 by 6? Now, I strongly encourage that you use my answer to save you some time. Now, the second problem is a little bit more subtle, is what fraction of all squares are even? What fraction of all squares are even? Now this is interesting because you have to calculate the total number of squares, which is something I mentioned earlier. It's a classic math challenge question, is how many squares are there, because it's like a bunch of 3 by 3s, and then there's a fewer number of 4 by 4s, and then there's only one 6 by 6. There's a really, really neat result in this, which is quite cool. The third question is, can you extend these ones for an n by n? So if I just tell you it's an n by n square of consecutive numbers, could you find out how many even squares are there, and also what fraction of squares are even? And then what happens as n gets really big? And leaving possibly the best to last, this is my sort of deeper question to make sure that you really understand where these numbers are coming from. So let's take a really simple 2 by 2. Now how many even squares are there in it? Well, there's 1, and there's 2, and then there's 3. So there's 3 in total. Now, is it possible to swap any of these 2 around? So for example, maybe I swap the 2 with the 3. Does this affect the total number of even squares? No, it does not. But now let's try something similar with a slightly larger grid. Now we know how many even squares are there in it. Well, there's 4 evens, and then there are 4 2 by 2s. So there's 8 even total squares. Now let's just see if I swap round one of the evens and one of the odds. I'm just going to choose them kind of at random. I'm going to swap the 2 with the 9. Now let's see how many there are now. Okay. This one here is no longer even. This one here is no longer even. This one here is even. And this one here is odd. So we've actually got much fewer. We've only got 1, 2, 3, 4 even numbers, and then only 1 square where it's still even, 2 odds and 2 evens. So my question for you is, if we have in general an m by n consecutive grid like we had before, is it ever possible to exchange 2 numbers and increase the number of even squares? If you found this helpful or interesting, please hit the like button, let me know your thoughts in the comments below, and of course subscribe so you won't miss the next video.